Okay, so we're going to continue with phasors. Hopefully the projectors will be happy. And just getting caught up here. So we had explored the background of, oops, I don't want to do that, complex numbers. And we had solved a few, and then, so the idea of a complex number, of course, is that you have a real and imaginary part, and you can think of a complex number plotted in the complex plane, and you can think of it as a vector with a magnitude and an angle. And we just introduced phasors on Monday briefly, and we showed how you can think of if you think of that vector, which represents a complex number as an amplitude and a phase, if you think of that as representing the phase of a sinusoid, then you can imagine that that vector is just sort of rotating around the origin with time. And we find it really convenient to think of the initial phase and just pull out the amplitude and the initial phase and stick that in a complex number, which pretty much represents the location in the complex plane where the sinusoid started off at time 0. And this thing is going to be rotating around the origin as the sinusoid progresses. But we don't need to worry about that. We're just going to look at that phasor, which has no time component in it. We strip off the time component, and we just think about this as a complex number with an amplitude and a phase. And this becomes basically all we need to do to represent a sinusoid so that we can do mathematical operations on sinusoids using these complex numbers. And for some reason I thought I had marked this up, but I guess I didn't save it. So this is the, we solved this problem, right? We did this one, right? Did we do this one? Yeah. And basically the phasor transform just says, real briefly as a recap, we use like boldface capital I's to represent the phasor version of a time domain current, and you basically just strip off the magnitude and the phase angle and say, huh, that's a phasor. And that represents our current in a timeless domain. There is no time in phasors. It's just this constant number. And when you have a sine, you can subtract 90 to get that to a cosine, and then add 180 to flip the sign of that thing. So V is going to be 4 angle 140, because I subtracted 90, then I added 180, so I added 90 to get 140 degrees. And we also looked at how these things lag and lead, which you can do, you can pull up I can pull this up to show you at least. Maybe that'll take a while. And the idea is that one sinusoid will be in front of the other sinusoid. This is taking much too long. Easier for me to just draw it out. And when you have two sinusoids and you're sometimes we're interested in knowing which one is leading the other, the one that has the larger phase angle, if this is A1 angle phi1, and this is the phasor for A2 angle phi2. These are actually going to be now time domain, but you could represent these as phasors. The question is if phi1 is greater than phi2, that implies that that phasor 1, that this guy is leading. Phasor 1 or sinusoid 1 is leading phasor 2. And we did a little bit about that in in lab yesterday. So you actually cranked through a whole example. We're going to just sort of reproduce what we sort of did in in lab yesterday, in lecture today.
Is this where they're doing physics where it's ICE or something like that, that acronym? ICE?
I've never heard of the acronym ICE in physics. What does that stand for?
I'm not sure. I thought that's when we got to phasors. Yeah, I'm not sure. But there was another one to go with it. It was about the reading and stuff.
Oh. Well, I'm going to have to search that up now. Let's see. ICE for phasor. Let's see what that means.
Or maybe ELI. Is that one of them? Really?
Oh, you're probably talking about capacitors and inductors, right? L means inductor, and I. So E could be V, voltage, right? Potential. E is usually potential in physics. They usually use E for that, right? Electrostatic potential.
Is that phasors or no?
It might be.
Okay. Just came in on it.
Yeah. Well,
I see something that said ELI and ICE on the pictures.
there we go. Yeah. Well, it was there briefly. Yes, that's what it means.
Phasors?
It has to do with phasors, and this has to do with the phase relationship of inductors and capacitors, and it's relating which one's leading the other when you have a capacitor or inductor. Yeah, that's what that mnemonic means. Yeah, cool. I can't pull it up here because somehow we have to always assume that technology is going to work so occasionally. So be aware there's a difference between the time domain and the phasor domain. V of t is actually a sinusoid, and V is in the frequency or phasor domain. It's the frequency domain because we're using frequency to determine the value of V, and or also called the phasor domain. And we've removed time from it. So it's just going to be a number, like in a complex, in the real and imaginary complex plane. It's just a single number, whereas the V of t is your actual sine wave that's going up and down. Okay? So V has no time dependency. Phasor V has no time dependency. Also, V of t is always real. Okay? There's no imaginary term on a V of t sinusoid because you can't measure it. V of t you can actually measure with your analog discovery scope. You can actually see that waveform. But you can never really measure a phasor. I mean, you can infer what the phasor is, but you can't see it directly. It's in the complex plane. Another important thing to realize is phasor analysis applies only when the frequency is constant and between the two different points. Like if you have a sinusoid of one frequency and a sinusoid of another frequency, you can't process them by converting them both into phasors because the phasor only applies to a certain frequency. So you can't really mix frequencies when you're doing that. So you can only do phasor analysis to two sinusoids when they're at the same frequency. So this slide shows you the alternative in case you're having a little resistance with this idea of phasors. This shows you, well, okay, suppose you don't want to use phasors. You could derive the differential equation for these circuits, which in this case, this is a second order circuit. You have a second order differential equation. If you're driving it with a sine wave, it looks like they might have done a source transform here. I don't know what this deal is here. Why is that? Anyway, it's not going to be fun, right? You're going to really have a hard time dealing with these crazy differential equations. So the phasor transform method makes it so much easier. So what we do is instead of deriving differential equations for these circuits, which are really the governing equations, we just transform everything into the phasor domain, the R's, the L's, the C's, and the signals, and then we just do KCL DC analysis to solve for the VO phasor, and then convert that back into the time domain. So again, this is a little bit redundant, but here we are, Ohm's law in the time domain. I of t equals Im cosine omega t plus phi. So V of t, if you're running a sine wave into a resistor, V of t is just going to be R times that current, right? There's no phase lag or anything across a resistor. And the same is true in the frequency domain. If we think about this current as a phasor, it would have a magnitude of Im and a phase angle of phi, which is this guy right there. And in the phasor domain, the voltage associated with that current is going to be R times the phasor I. Kind of bold these in a little bit, make them stand out so we don't mistake them for anything else. Which means that the voltage is going to be R times Im times with an angle of phi. And this is the same effect as in the time domain. Inductors, as we know, V equals L di dt for an inductor. So suppose I of t equals Im cosine omega t plus phi. V of t is going to equal L di dt, which when you do a fair amount of trigonometry, maybe I can skip through some of this because we saw that yesterday. Are you guys comfortable with that if I kind of move through this fast, or do you want to go see that again? You're really curious how this actually works, this law? You're not saying anything. So the derivative of the cosine is the minus sine, right? It's interesting, right? So in other words, we're just following this rule here that V equals L di dt, right? I took the current and I took the derivative, multiplied it by L, and that's going to be my voltage across the inductor. And with a little bit of manipulation here, I can say, well, I got to get that sine into a cosine, right? How do I do that? Well, I can subtract 90 degrees. So that's a cosine of omega t plus phi minus 90 degrees, right? And then I've got a minus. I could turn that into a plus by adding 180 degrees. So then I have plus omega L Im cosine of omega t plus phi plus 90. You with me on that? And therefore, if I say that I equals Im angle phi, V, phasor V for that same situation, I'm just going to say, well, I just take my I and turn that into a phasor, and I get, I add 90 degrees phase shift. So W times L times the magnitude Im, and I've got a phase angle here, not phi anymore, but phi plus 90, right? Okay. And but a 90 degree phase shift, if you put this in our Eulerian exponential form, that's Im e to the j phi plus 90, right? And you can then, stop me if you've heard this one before, you can split those apart, right, because they're exponents, right? And e to the j 90 is what? Complex plane. You're 90 degrees away from the origin with a magnitude of 1. What are you at? If this is 1, you're 90 degrees. What do we call this? Complex plane, real axis, imaginary axis. You went 90 degrees, straight up, 1 unit. What value is that? It's j. So e to the j 90 just becomes j, right? So this is just j. And you plug that in and you say, okay, so we have W, L, I, M, e to the j phi times j, which is omega j omega Li. Means if you give me a phasor current that the inductor is seeing, I can take that current, multiply it by j omega L, and tell you that the voltage is going to be 90 degrees out of phase. It's going to be actually 90 degrees ahead. It's actually plus 90, right, of the current. So the voltage is going to be leading. And here's where Brock's acronym comes in, right? The voltage is going to be 90 degrees ahead of the current, right, because we're doing phi plus 90, right? So we could say VLI, or in physics, ELI. You have the voltage, and then you have, of course, an inductor is ahead of the current, right? Well brought up there, Brock. Okay, so yes, and the capacitor works the same way, just kind of speeding up a little bit. You could actually do the same analysis here, and here, in this case, we're giving a cosine for our voltage, and then we take the derivative of that. Again, giving a minus sign, we add 90 degrees and so on. And what ends up happening is our phasor current I is j omega c times phasor V. Because, again, this is the 90-degree phase shift we model with just putting a j in front of it and just omega c, and this whole here is phasor V. And that's the same derivation as the inductor. But since we normally express these as V equals something times I, then we can derive our essentially Ohm's law for the capacitor is I over j omega c. Or if you don't like a j in the denominator, you can multiply top and bottom by j, right, which gives you a minus 1 in the denominator, or V equals minus j omega c I. And now this is across a capacitor, right? And what this means is the voltage is going to actually be 90 degrees behind the current, because the current here is what's advanced, right? So that folds into Brock's acronym ICE, where E again is the potential. The current across a capacitor comes ahead of the voltage. So the current leads the voltage in the capacitor. That will help because I often forget that, and I'm going to remember that acronym. And what that looks like in the complex plane basically is saying if you have a resistor, well, V is just in the phasor domain, phasor V, phasor I, they're related by phasor V equals I times R. It's the same phase, but a different amplitude, right? You have to take I, multiply it by R. So the V vector is going to be probably bigger than the I vector, but it's going to have the same phase. And they're going to be spinning around in phase with each other. If you've got an inductor, though, the voltage is going to be j omega L times the current, and that j is pushing a 90-degree phase shift ahead of the current. So the voltage is going to be leading the current by 90 degrees, right?
How come they spin around?
They spin around because it depends on what you're sort of thinking about. But when we did the phasor transform, we're basically starting with a V equals V of t equals cosine of omega t plus phi, some Vm times the cosine omega t plus phi. Now, in the phasor transform, all we really need to know about is the initial phase. So we throw out the omega t part, right? So we say, well, that's the real part of Vm e to the j omega t plus phi. Right, this V of t time, sorry, it's a little bit of a scrawl here. Vm cosine omega t plus phi is the real part of this exponential form of a complex number, Vm e to the j omega t plus phi, because this is cosine omega t plus phi plus j sine omega t plus phi, right? And we just want the real part of that to get this time waveform. Well, this is a complex number, and if you keep we normally throw out, when we do the phasor transform, we throw out the time part because that doesn't really help us with doing any of the any of the combination. We've got to like combine these different signals at different phases. The omega t doesn't really have a play in it. But if you think about that omega t being still there, then the actual location of this vector, the phase angle, the entire phase angle, if you call that theta, is omega t plus phi. Theta is growing linearly with time, and it's gonna, if you keep looking at it in future times, the phase of this thing starts rotating, right?
Wasserman hates how it's spinning around, so it just shows you without it.
Can you say that again?
Wasserman hates how they spin around, so he shows everyone how to, I guess, do it without them spinning around.
Okay. Well, and I tried to pull up an animation which didn't work, but basically you can imagine when that thing rotates, and we're just seeing a projection of that rotating phasor, on the real axis. But right, in general, the phasors themselves don't rotate when we do these analyses. So, I guess Homer has a point there. But it does help understand. It helps kind of explain how you can get a cosine from this single complex number, because in reality, things are changing. And then the same thing is true for the capacitor. So I equals j omega c v means that the current is leading the voltage by 90 degrees. This is the summary table expressing the relationship between the time domain and the frequency domain for R's, L's, and C's. I'm not sure, but this might actually be on your table handout. Do you have that? I have to go check. Yeah, is it on the RC table? Or the LC table? Oh, no, but you might want to add it to there. Okay, now we're going to do an example. So this is a good one. So this should be on your problem handout. Example 7a. So if the current I of t is 5 cosine 100t plus 30 degrees, and we're applying it to a 2 millihenry inductor, so here is our so we're applying some I of t to this thing, and we want to know what the heck is v of t going to be when we apply this I of t. Oh, do you want to see those again? So V equals j omega Li for the inductor. That's basically Ohm's law for the inductor. And normally it's written with a minus sign for the capacitor. So V equals minus j over omega c times phasor I. Okay, we got it?
The symbol down there is IV, or what's the bomb right here?
This thing is a V. It's a bold-faced V for phasor. So I'm putting these 2 slashes, something like that. That's not IV, that's just one V. You'll see that in your book. It'll be like a bold typeface. Okay, so if we are going to try to figure out this problem here, I of t, V of t, we want to figure that out. Well, in the phasor domain, we know the phasor relationship for an inductor is V equals j omega L times I. And since we can read off phasor I pretty much directly from there, basically what it's saying, our voltage is going to be J times 100. This is going to be omega, the 100t, right? So omega equals 100, and phi equals 30. So it's going to be J times 100 times 0.002 times I. And I is just a phasor with a magnitude of 5 and an angle of 30 degrees. And this tells you when you multiply all this together, that's basically J times 1 angle 30. And in general, we don't want to have J in our phasor answer, so we can work that in. This J represents a 90-degree phase shift, right? So 1 angle 90 times 1 angle 30 is going to give us 1 angle 120 degrees. So this step, again, is realizing that what this J is that we're multiplying this 1 angle 30 phasor by can be represented as just a, in vector form, it's a magnitude of 1 with an angle of 90 degrees. And this is our answer for the phasor voltage, which means that doing the inverse phasor transform, our V of t is just 1 times the cosine of omega t, well, which is 100t, plus 120 degrees. Okay. Likewise, if we're applying a voltage across a capacitor, we want to know what is the current. Well, we know that V equals minus J over omega C times I, or I equals J omega C times V. Depending on how you deal with that J. Again, omega equals 100, and C equals, in this case, 50 microfarads, so 50 times 10 to the minus 6. And V equals 6 angle minus 30. That's just taking this thing and doing a phasor transform. So therefore, I is just going to be J times 100 times C, which is 50 times 10 to the minus 6, times 6 angle minus 30. And cranking that all through, it's J times 0.03 angle, 0.03 angle minus 30. And again, that J is a 90 degrees phase shift, so you can write that as 1 angle 90. And what you'll end up getting is 0.03 with an angle of 60 when you add these things together. And doing the inverse transform, that means your current then is going to be, you can do this in milliamps because this is in amps, so 30 cosine of 100t plus 60 milliamps. Okay, questions? So the more general term of what we're doing here is that we're determining the impedance of a component or maybe a network of components in a circuit. And the definition of this new concept, impedance Z, is kind of like resistance, except we now are in the complex domain. And it's the ratio of the phasor voltage to the phasor current. So this is basically Ohm's law in the phasor domain. So Z, impedance, is going to be phasor V over phasor I, which in general is going to have a real part and an imaginary part. And R is the real part, which is considered the resistance, and X is the imaginary part, which is considered the reactance. So it's a new term. This is called the reactance. There's a lot of technical terms for these things. Resistance. We also have a term that the reciprocal of that, just like we had conductance, which is the reciprocal of resistance. We have admittance, which is the reciprocal of impedance. And Y is going to be 1 over Z or I over V. And there's a term for these things too. I forget what that's called. Well, the reciprocal of R is conductance, and the reciprocal of reactance, I'm not sure what that is. Oh, no, that is admittance. Susceptance? I can't remember. And again, this is if you're adding to that table, you might again think about calling another quantity here for Z, which is the impedance of these different devices. The impedance for resistance is R. For an inductor is just j omega L. For a capacitor is 1 over j omega C, or minus j over omega C. Tends to be a little bit easier to keep the j in the numerator. And then admittance is the reciprocal of all that. Okay. And a little bit more about impedance and admittance. There are some interesting observations we can draw when we look at a inductor. Basically, this impedance now, it has a frequency component to it. So the impedance of an inductor or a capacitor depends on what frequency the sine wave is that's hitting it. So if you're talking about a DC signal, the impedance is going to be really small, because when omega gets really small, the impedance gets really small, right? We're just going to multiply this whole thing times omega. And in fact, when omega goes to 0, Z goes to 0, which means that the inductor is kind of like a short circuit at DC, which is kind of how we've been using it when we do these first order circuits or second order circuits. But when omega gets really large, the impedance is also going to get really large. And you can see that as omega approaches infinity, so does Z. So we have basically an open circuit at high frequencies for an inductor. And capacitors do the opposite, interestingly enough. So since it's 1 over j omega c for the impedance of a capacitor, omega is on the bottom. So when omega approaches 0, the capacitance approaches infinity, which means a capacitor kind of looks like an open circuit at DC. And when omega gets really, really large, the Z goes to 0. So the capacitor looks like a short circuit at high frequencies. And it's these frequency-sensitive behaviors that we capitalize later on. We show you how you can make like frequency-selective circuits. You can make filters to actually pass certain frequencies and reject others, which is really important for audio applications, and a lot of all communication systems need filters of some sort. Oh, thought we were going to make it. We only have 7 more minutes, and you know, I nervously moved the computer about 2 minutes ago, but I don't think that caused it. Well, it's back. Let's not explore any further than we need to. So the beauty of this is now that we know how to convert the components into the phasor domain, we can transform a time domain circuit completely into the phasor frequency domain, solve it there, and then transform it back to get our time domain answer. The beauty is once we do all that stuff, the same KCL laws, nodal analysis, mesh analysis, Thevenin equivalence, all that stuff works the same when you're dealing in the phasor domain as you are in the time domain with DC circuits. So, for example, 8, for instance, we're given a sinusoidal exciting an RL circuit. We want to find V of t and I of t. The first step is let's find, so I is the current going into this thing, and V is the voltage across that inductor.
So on circuit lab, it's not going to be a plus or minus, right? It'd be the wave or something?
Yes, yeah. Circuit lab is nice, but it doesn't do these fixed frequency analyses very well, although I haven't played with it that much. Circuit lab kind of wants to do a frequency sweep when you have an AC circuit, so you can see like the frequency response of it. It doesn't do so good at single frequencies, and it doesn't really tell you the phase, I think. I haven't played around with it that much in that aspect. But yeah, the circuit lab does have these components for alternating current signals. It won't be plus or minus, it will be a squiggle in it. So our solution, in order to find I, if we knew what ZL is for this entire network, we could take and find I by doing phasor VS divided by phasor ZL, or impedance ZL. ZL is not really a phasor. So the formula for ZL is going to be, well, actually this is just the inductor, so we're going to call this guy, oops, this guy here. We're going to replace this with ZL. And ZL is just J omega L. And that means we are J, omega here is 10, and L is 0.2. And that reduces to just J2. Now the total impedance, which I was calling ZL, is really going to be ZT. In other words, the impedance, if we remove that source, it's the impedance looking that way on this circuit. Draw it that way. Arrow pointing to the right, meaning it's the impedance from this terminal to that terminal. And basically, it's just series impedances, right? ZT is just going to be the resistance R, 4 plus ZL, which is 4 plus J2. We can turn our input signal into a phasor, so we'll call that phasor Vs, which is just 5 angle 0, right? Because there's no phase angle here, V equals 0. And then we can use Ohm's law to find phasor current, Is. And that's just going to be Vs over Zt, which is going to be 5 angle 0 over 4 plus J2. Now, it's a complex number. You can't just treat it the same way as we used to. It's a little bit harder than a DC circuit. But if we take this complex number and turn it into its polar form, we're going to have a magnitude of 4 squared plus 2 squared, square root of that, and an angle of the arctangent of 2 over 4. If you have a calculator to make that easy for you, or MATLAB, that's all great. But that turns out to be 4.47 with an angle of 26.57 degrees. And doing that division, we get 1.118 with an angle of minus 26.58 degrees. 5758. Oh. Leave it as something like that. Which means Is of t is the inverse phasor transform of that. So that's just going to be 1.18 cosine of, bringing your omega back, 10t minus 26.56 degrees in amps. And finding out V, phasor V, I almost put V of t. Phasor V is just going to be ZL times the phasor current. And that means we're going to multiply this 1.118 angle minus 26.57 times J2, which is a 90-degree phase shift and a magnitude of 2. So we get twice the amplitude plus 90 degrees on the phase. So that turns out to be 2.24 or something like that, with an angle of 63.43 degrees. So that's basically how it's shaping up. We'll do some more examples tomorrow. Mm-hmm. Sure. Okay. See you tomorrow.